In continuation, magnetic effects of current, and in the previous class we have discussed about the Lorentz force. Whenever a current carrying conductor in the magnetic field, then the value of force can be calculated. That is always given by ILB if L is the length. The same principle we have to use. Now the topic with you is that we want to find the torque experienced by a current rectangular loop when it is kept in uniform magnetic field. So uniform magnetic field means I am having the north pole, south pole here like shown this way. In the uniform magnetic field, field is always from north to south. So this is the direction of the field. I am keeping a rectangular coil, simply means a wire whose rectangular loop is made. So rectangular loop is made of the wire and it is kept in the magnetic field, that is the uniform magnetic field we are keeping the loop. Now it is your choice if you want to make the current to go in whatever direction, like you may take it in the anti-clockwise direction, you may take it in the clockwise direction. Here I have supposed in this diagram, if you see, then the current is moving in this direction. It means P to Q, then to R, S and back to P, this way. So of course we need to have a source of the current. That source of the current can be a battery. So that you need not show always in the diagram. So you need not draw this diagram. And of course here the direction of current is also different. So whatever you suppose, you can take the direction of current in whatever way you want. And I am focusing on this diagram, which this much diagram you are supposed to draw if you are asked with this derivation, that you have to find the torque which is there. Now what we are supposing? We are supposing let theta is the angle between the plane of the loop and the magnetic field. Magnetic field is the uniform magnetic field. So uniform magnetic field is always shown by the equidistant parallel lines. This also we have already discussed. Now the thing is, when you are keeping the rectangular loop in the uniform magnetic field, then the magnetic force will be produced, and the direction of magnetic force you can always find by using Fleming's left hand rule. So left hand rule, it means if I want to find the direction here at this point on RS due to this point on PQ, then the magnetic field, it is given by this line, current is given by this line. So you have to see that this thumb will give you the direction of the force. So at this point we are getting the force is acting in the inward direction. Same way if you go that this is the direction of the current, then it will come in the, if you take for this position, then this is the value of the current is going in the upward direction, and then you see here's magnetic field, and then you find the direction of those. So that you have to find the direction of the force always by Fleming's left hand rule, that you have already done. So you can find the direction. Here also if you want to find for PS or SP, the direction of current is from S to P. If you write by using the formula from the Lorentz rule, then it is current into the L into the B. L here, the length of this side PS is taken as small b as it is shown in the diagram. So it can be written by B into capital B, or I can write it as IB capital B sin theta. Capital B is for the magnetic field, small b is taken for the length of this side PS. Similarly, if you find for the F for QR, then also you can write the value. Now this force, if you find the value of the force, it is coming in this upward direction. For this, the force is coming in the downward direction, but it means equal and opposite forces, as magnitudes are same, but the directions, they are coming opposite. So, and they are acting along the same line. So what will happen? They both are going to cancel each other and no torque will be produced because of the current in this side PS, or you can say SP and QR. these because of these lengths no torque will be produced, because forces produced, they are coming equal and opposite. But now if you see, because of this PQ and RS, what is happening, that you need to see the values. Again, formula is same. If I am taking this length as L, PQ length as L, then in place of small b, I will be writing the length of the side, which is L into L cross B. So I am getting LB sine 90, because now the angle between the and this side is 90. So earlier the angle was theta between the plane, and now the angle is 90 degree. So you are getting the maximum value, it means, of the force, that is equals to ILB. But if you see at this point, the force direction is inward. This point force direction is outward. Again, you can find by using Fleming's left hand rule. Both are equal in magnitude, opposite in direction, but they are acting along different lines of action. So they are going to produce the torque. So I have to find the value of the torque, it means, which will be produced because of these sides PQ and RS. Now if you want to find the torque, then you know the formula, that is given by either of the force into the perpendicular distance between them. This is the direction of the force. If I am taking FRS, this is the opposite FPQ. Now the direction here, theta, we took the angle between this plane of the coil and the magnetic field. So if you take the perpendicular distance, this is the distance between the two forces, that is equals to Pn, which is coming out to be equals to B cos theta. Now if you take the angle phi here, phi is the angle between the normal to the plane. This is a direction shown for the normal, and this is the magnetic field. Direction of the normal and the magnetic field, if you find, that angle is phi, we are supposing. So of course you can either give the result in terms of the ILB B cos theta, or of course length into breadth of this rectangular coil can be written as the area of the coil. So I can write it as NIAB cos theta. If I take, in place of one turn, I take n number of turns. Capital N is the total number of turns. If I am taking phi as the angle, then you can see this theta plus phi is 90. So I can write this formula for torque is given by IAB cos 90 minus phi, because theta is equals to 90 minus phi, or I can write it as NIAB sin phi. So most of the time the question is always, because when you are taking the direction between the normal and the magnetic field, that is a general case it is taken as. So you need to understand that if they are taking the angle with the plane, or they are taking with the normal to the plane for the direction of the magnetic field, that you have to see. And of course you should be able to find the direction of the force by using Fleming's left hand rule. That should be clear. So this is the result, it means, with me. Now if this phi is 0 or phi is 90, if phi is 0, then torque will be 0. It means if you are taking, the magnetic field is also acting normal to the plane. Or if this phi is 90, then you will be getting the maximum. So that you can write, of course, in the vector form. If you want to write the torque in the vector form, it can be written as Ni can be taken out, area vector into the magnetic field vector, and this I into A, that is equals to the magnetic dipole moment. So if you want, you can write torque in terms of the magnetic dipole moment also. Like we are having electric dipole moment, similar to that we are having the magnetic dipole moment. Of course, it means you should be knowing, these are the points to note with you, that you can find the torque. Again, torque direction will be perpendicular to your A and B vector, that you can find by using the Fleming's right hand rule or Maxwell screw rule you can find. Simply the direction, cross product direction you can find. So if you know the direction of the area vector, you know the direction of the B, then you can find the direction of the torque. And if phi is 0, then torque is 0. When phi is 90, torque will be maximum value. And units of magnetic field already known to you, they are Tesla. And torque, it is always measured in Newton meter. So from its basic formula, because torque is either force into the perpendicular distance. So these are the points which you should keep it in your mind for the further use, because this same thing we in the moving coil galvanometer. In the moving coil galvanometer, if we talk, which we are using in various experiments like in the Wheatstone brush or in the potentiometer experiment, we are using galvanometer. That yours is of course a device which is used to find the very small value of the currents. So even if there is small current in milliamperes, that can be detected by the galvanometer. So galvanometer again is under two names. One which was given by D. Arsenault. He gave about the suspended coil type galvanometer. Now in the lab when we are using, that is Western type galvanometer, because of course the sensitivity of Western type is little less than this. This is pivoted coil type, but this is more rigid. It means it is getting harmed even if you are not using it properly or throwing the things at times. Throwing does not mean actual throwing, means you are not handling the things properly. So it is quite rigid, so can be used for the longer time, I can say. So but the basic principle, if I talk about the moving coil galvanometer, that is same either of who I may take. So this is the diagram which is simply to depict the thing. We are having the same rectangular coil and number of turns I may have, which is wound over this core, iron core, which is kept under the magnetic field, uniform magnetic field. We are having a mirror arrangement similar to like we use so as to avoid the parallax, so that pointer and its reflection, they are on the same side. These are the leveling screws which are provided. Here is a hairspring which brings the pointer back to its position. And of course, this is the terminal from which we make the current to pass. This is simply a diagram to show you. And the value of the torque, the basic principle is same for both. Either I am using the Arsenault or I use the Western type galvanometer. We are making the coil to rotate under the effect of magnetic field, and as a result the deflection is produced. And for the torque, if I say this is the formula of the torque I have derived, that is equals to NIAB sin phi if I go with the magnitude. And because of this torque, the restoring torque is produced, and this restoring torque is given by torque, it is equals to K alpha, where K is the restoring torque per unit angular twist and alpha is the angular twist. And as a result, when the current is made to pass from this coil, then current is coming directly proportional to the alpha, and this whole act as a constant K upon NAB sin phi. It acts as a constant which is Yours Galvanometer constant, can be written as capital G. This is the another way of drawing the diagram. You can always draw this diagram given in your NCERT book, which is the upper point view, which is giving you no need to make that previous diagram. You need to draw this diagram whenever it comes for you. This is the coil pointer which is moving on the scale. These are the permanent magnets, and this is the iron core. And of course this is the upper view, and actually we are having the iron core, we are having the rectangular coil like this, and hairspring is there to bring the pointer back to its position. Of course pointer, we use the phosphor bronze coil here, so that because it is able to come back to its initial position quickly without your elasticity, the thing which you have studied earlier in 11th class also. Now the field which is there, that should be the uniform radial field, then only we get that torque is directly proportional to the alpha. And for that, on you get the question also that why the magnetic field should be radial. This is again the same diagram, upper view it has been given. So if theta is your phi, here we took the angle between the normal and the magnetic field. If it is 90, then only we get the maximum value of the torque. And I can write K upon N AB alpha. This K upon N AB, it is equals to capital G, which is galvanometer constant. So this is possible only when I get sine 90. It means phi should be equals to 90. It means I should say angle between the normal to the plane of the coil and the magnetic field should be 90 degree. Or I can say that the angle between the plane of the coil and the magnetic field is 0. So whatever method you can say, then only we make the field is radial. It means we get the current is directly proportional to alpha, and that is why we are able to get the linear scale. This is lamp and scale mirror arrangement is given just to make you clear that we are able to get the reading without having any parallax. That you have to keep it in your mind. And if we are not having the radial field, then I will not be directly proportional to alpha. And so it means I will not be able to get the linear scale. And if I am not getting the linear scale, then I will not be able to give the correct result. So for that, the field should be always radial. You can be asked with these definitions. Current sensitivity of galvanometer. It is the deflection of the galvanometer per unit current. It means alpha upon I. So it is equals to NAB upon K. And if we have to give voltage sensitivity of the galvanometer, it is the deflection of the galvanometer per unit voltage. So alpha upon V you have to write. I can convert this galvanometer into ammeter. So in the lab, when we are using ammeter or voltmeter, we can get it by the help of galvanometer. That can be taken as a project work also. So galvanometer, if you want to convert into ammeter, you have to connect a small resistance parallel to the galvanometer. And when you are connecting it like this, current I is made to pass. Then if I am supposing Ig current is passing through galvanometer, then from the shunt resistance or the small resistance, the current which is passing will be equals to I minus Ig. But potential difference is same. These both are connected in parallel. So I can write I minus Ig into S. It should be equals to Ig into capital G. Or I can write S equals to Ig capital G upon I minus Ig. So this is the formula which can be asked in the numericals, that what should be the value of the shunt resistance, and they may give you the value of the range of the ammeter. Resistance of the galvanometer, of course capital G can be given. Capital G, here we are taking the resistance of the galvanometer. Similarly, you can convert a galvanometer into voltmeter simply by connecting a resistance in series with the galvanometer. Capital G, we are taking the resistance of the galvanometer. R is the external resistance which is connected in series. Then if you see the potential drop across this, these both are in series, it means V can be written as Ig into capital G plus R. Or you can find the value of capital R, the resistance which is to be connected in series with the galvanometer. That can be the question with you. So that will be given by V upon Ig minus capital G. So these formulas should be known to you. Of course, can be used in the numericals. Of course, you should be knowing about the difference between the ammeter and voltmeter. Always we are connecting the ammeter in series because it is a low resistance instrument, while voltmeter is always connected in parallel in any circuit because it is a high resistance instrument. Of course, resistance in terms of galvanometer resistance, if you want to write, the values for the ammeter are Gs upon G plus S because both the resistances were in parallel, while here the resistances are in series, so the value of resistances can be written. And of course, for the ideal ammeter, if we speak, then the resistance is 0, while the resistance of ideal voltmeter is infinite. It means it is greater. And you can always change the range of the voltmeter, but the range of the galvanometer cannot be decreased because you are connecting a smallest resistance in parallel and that cannot be reduced further. So all these points you need to keep it in your mind, which of course can be asked in the conceptual questions and otherwise for the use in the practical doing the experiments. Keep to this. Thank you everyone.